Thank you all for the opportunity to speak. Yes, so I'm going to tell you, like, this will be kind of very much, if you were here last week, kind of about that type of stuff. And I should also always say, let's see, what do I always have to say? Everything I'm going to say I talked about in great detail with David Reiter. It's sort of all the good ideas might be his, and with other people like Konstantin and so on. And it's very hard to talk about ideas and conjectures when the people who had those ideas and conjectures are in the room. I'm not the first person to make this observation, so I apologize if I misattribute things, especially. Roughly what I want to do today, I'm going to start by sort of reminding some things that we learned last week, and then I will say some brief comments about what David and my universal target category. David will give a lot longer discussion of that tomorrow morning, tomorrow afternoon if you're on the wrong ocean, on the wrong continent. And then I'll say some more words. And the punchline of my talk, so that you can now ignore the rest of the next hour, is that there have been various proposals about sort of hoping for dual to smooth bordism categories. And I'm going to say those proposals are almost correct. I think that we should have said what there was a comment at the very end of Mike's talk last week from Friedman that we should have been working with piecewise linear things from the beginning. I'm going to try to advocate that perspective. So I also want to say the sort of main driving conjecture is sort of very reasonably Kitaev's, but I learned it from papers of Kapustin's in 2014. So I've put his name up, and I don't know the history. I wasn't paying attention at the time. So okay, so let me tell you the sort of the problem that many of us have tried to investigate. We want to study the space, the collection of invertible gapped phases of matter. And maybe I'll write in phase n for that set for say space-time dimension n. And Kitaev gives a wonderful argument in a lecture in 2013 that says that this collection, like there's some space of those that depends on n, and those spaces, as you make n get bigger and bigger, these, Kitaev says, compile into an omega spectrum. And I thought it might be nice to even remind that argument. So here's what Alexei says. So he says, okay, there's sort of, what does it mean to say you have an omega spectrum? It means that the n-1th space in this list is the loops in the nth space in this list. That's the definition of omega spectrum. I should give you a way that these two spaces are at least homotopy equivalent. So Kitaev says that there's sort of an easy direction, which is to give the map from loops to phases one dimension lower. And the easy direction, you sort of say, oh, suppose I have a loop. So that starts in the vacuum, there's nothing going on. And then it's sort of, the phase sort of changes in some continuous way, like it becomes orange, and then it becomes red, and then it becomes purple, and then it goes back to vacuous. And he says, whatever you mean by invertible phase, you should be able to run this adiabatically in space. You should be able to take the big room and just like put the vacuum phase over here, and then in this region of space, run the sort of orange version of the phase. And so you have a sort of continuous family in space of phases. And then you just zoom out, and you zoom out again. And eventually you see a sharp defect from the vacuum to the vacuum, and you identify sharp defects with phases one dimension lower. Okay, so that's a nice argument in one direction. And obviously the fact that I can run it the other, yes?
It also works for non-invertible phase.
Well, I don't know what a non-invertible loop is, because I don't know. I live in sort of out in Canada, and we don't have all these one-way streets in Boston. So for us, if you could drive one way along a street, you can definitely drive. You can just sort of back up,
For every gap phase, you can just deform the gap phase and form.
So what I think
do not continuously let the gap close. Yeah.
So I think what I more strongly believe is that I do believe that there's some sort of higher category of gapped phases and gapped interfaces. And this argument more generally is showing that that higher category satisfies a condition that's either called completeness or univalence. But I'm going to focus on this part of the story. Yeah. So the harder direction is to, in my mind, I think the harder direction to see why this should be true is to go the other direction. So if you actually just sort of give these maps that I told you from like loops of something to something else, you can, the adjoint of loops is suspension. And so this is sort of the same data as to give a map in from some space to the suspension of some other space. And those together are like what you might think of as a suspension spectrum. So you might already pat yourself on the back and say, I'm done. I've written down a suspension spectrum, and you'd be wrong, because suspension spectra, to use those as a model for spectra, is a slightly subtle thing. You have to invert sort of stable equivalences. Omega spectra have the advantage that you don't have to do anything. They just model spectra on the nose. That's sort of the math advantage. But the physics advantage is I don't care about the stabilization of these spaces. I don't want to take an infinite limit. I want to study the actual space of 7-dimensional invertible faces. And if I had to take some limit before I can use stable homotopy theory, then I've lost information. I'd really like to know this is an equivalence and not just a map. So what Alexei says to go the other way is the following. So suppose I had an invertible phase in n-1 dimensions. What does it mean that it means that it's invertible? It means that I can, out of nothing, just bubble the phase and its inverse next to each other. That's the definition of invertible. It doesn't cost me anything to create that. And then I could move them apart. Okay. So now what I'm going to do is I'm going to go, let's see, I think it might still be true that if you go to the Harvard Bridge, which is at MIT, and there's still these markings all the way along by smoots. And so at sort of at every smoot, I'm going to create a pair of an x and an x inverse phase, sort of infinitely far in space. And then I'll move them apart. And then I'll move them sort of in the other, sort of rearrange them in the other way. And I'm just swindling you. I'm just going to re-annihilate them. Okay, so let me just show you that movie again. So I just create them, and then I annihilate. So now Constantine's sitting in the very far back and not really paying attention and forgot his classes. And so what he sees is just something happened and then nothing, and then it went back to nothing. And so, so from very, very far away, this movie just looks like a continuous family from nothing back to nothing that went through something. So that's the other direction. And so this was the proof of the theorem, of Alexei's theorem, that says that this is a spectrum. And it's such a robust proof that it's the type of proof you can prove without having a definition. Unfortunately, it doesn't tell you much about this space, because for all I know, these spaces are contractible. I mean, the contractible space is a nice spectrum. And so now I need to sort of do more. So the conjecture question is sort of, which spectrum is this? This is some natural object in physics. It must be the same as some natural object in mathematics, because we know all the natural objects in mathematics. So which one is it? And as I said, I know from papers from 2014 by Anton, the proposal that maybe the spectrum is the dual to bordism spectrum. And there's various, you can always add variations. You could say I wanted fermionic phase, and then I would have said spin, or you might have said time reversal, or so on. And there's very good experimental evidence for this proposal, which is just it does match other approaches to classifying invertible phases in low dimensions. And like if you look at Anton's paper from 2014, he just says like, hey, we know we have this classification in dimension 0, we have this classification in dimension 1, and those homotopy groups, like I can recognize that sequence of groups. Reasonable guess, if I recognize a sequence of groups, maybe I've actually recognized the spectrum. Please correct me if I've said something wrong.
No, it's a question.
Yeah.
So there's a definite intuition from field theory about why bordism might occur here.
Yeah.
Which is Siegel's axioms for quick rotated field theory, particular topological field theory.
Yeah.
Is there any other intuition for why bordism might appear other than from field theory?
No, not that I can think of. Not yet. So Dan asked, so far I told you this experimental evidence is I go do other methods to try to classify, to sort of figure out what I think the classification of phases is, and I get some sequence of groups, and then I pattern match. And then Dan asks, okay, we could make an ansatz, and as I said, I think this ansatz is quite well formulated by Freyd and Hopkins in 26, a couple of years later. But I mean, it's sort of implicit in what Anton was certainly writing, which says that you might hope, there's a big question, a big if, but maybe it's true that phases of lattice models, that phases of materials that somebody like Alexei cares about, maybe those in some mysterious way match phases of continuous field theories. And maybe continuous field theories you've just sort of declared to be something about bordism categories. But there's some big assumptions implicit there. And so one way to say that is maybe there's some kind of secret rotation or Lorentz or Wick rotated rotation symmetry that emerges when you talk about the phase of a material, even though microscopically materials never have continuous symmetry. You do sort of expect at least some of this. You expect, when I said I was implicitly talking about like gap topological phases. So whatever gapped topological means, it certainly should be the case that kind of, if I wiggle just a little bit, nothing happens. But in homotopy theory, we do know that just because I can wiggle a little bit and nothing happens, that's not the same as saying that going all the way around is trivial. You might have picked up higher homotopy when I did that. So there is a sort of real non-trivial statement here. I mean, no matter who you are, whether you're a homotopy theorist, there's a non-trivial statement, or a condensed matter theorist, there's a non-trivial assumption with this. So another ansatz that Mike and Dan really kind of made very precise was they said that at least for invertible phases, let's just posit, well, maybe not invertible phases. Let's switch gears. Let's talk about quantum field theories. Quantum field theories is something where I know what it means to talk about partition function, especially after Wick rotating. I know what it means to talk about them. And Dan and Mike say, let's just assume that partition functions of invertible quantum field theories determine the quantum field theory up to isomorphism. Maybe there's a bigger assumption that this is part of, maybe not. Let's make at least this assumption. And then what they explain in their paper, and I'm not going to remind all the details of the argument, is that if you make this assumption, you can quickly talk yourself into believing that invertible phases of n-dimensional quantum field theories now should be classified by some dual group to n-dimensional bordism. And that slide's wrong because I think MSON doesn't parse. I meant MTSON. The slide is wrong. I apologize. I left out a T. So please in your head go in and add T's. If you don't know where the T is supposed to go, then you could ignore this comment. But if you know these things, I'm sorry, I forgot a letter. So the T is either for Tillman or tangential, and I can't remember. So anyway, there's a problem with this proposal, which of course Dan and Mike are very aware of in their paper, which is that there's a perfectly good list of spaces, which is the list of spaces called the zeroth space of the dual to the nth Madsen-Tillman spectrum. These list of spaces do have some compatibility between them, but that compatibility is not an omega spectrum. I want to emphasize, like, these spaces arose from something in stable homotopy theory. These Madsen-Tillman spectra are spectra. I'm taking a list of spectra, I'm doing something funny with them, and then I'm saying that thing I got wasn't a spectrum. So because I did something funny. So this can't be the end of the story because Alexei told us I have to get an actual omega spectrum. This cannot be the correct answer. It can be close to the correct answer, but it can't be the correct answer. Yeah.
Which step does it fail to be a spectrum? So IZ is still a spectrum of entity here.
So this for each n,
surely
right.
that keeps a
So modulo the fact that I didn't write a T and should have, for each n, this is there is a spectrum of that name.
Yeah.
And so there is a space, which is the infinite loop space of the sort of zeroth space of that spectrum. And what I'm saying is that as you make n change, so what is a spectrum? A spectrum is a list of spaces and some relationship between those spaces. Here's a list of spaces with n changing. And as n changes in this list of spaces, I'm not getting a spectrum. Like this is it.
Is it easy to say what phase?
Yeah, it's the one that I called the hard direction before. So these list of spaces, I think, do compile into like they do have good suspension maps. But I think that they're not an omega spectrum. And I think if you stabilize to an omega spectrum, you get a dual of MSO and not dual of MSON, which maybe was what you wanted. I'm saying like this list of spaces is literally not the list of spaces in an omega spectrum. That's all I'm saying. Okay. So what fails is what I was calling the hard direction, the actual invertibility of the suspension isomorphism, like the isomorphism in the suspension isomorphism.
Oh,
So you have, this list of spaces has a suspension morphism. It does not have a suspension isomorphism. So, okay. So Freyd and Hopkins do another thing. They make another assumption about their problem. Their other assumption is something that they call reflection positivity. And I think it was probably Peter Teichner who pointed out that their definition of reflection positive was the same as what has for decades, well, at least a decade, been called a dagger category, a map of dagger categories. And roughly speaking, what they say is that there's sort of some extra information that I'd forgotten, which was that I wasn't supposed to work with arbitrary functors. I was supposed to work with functors that have the data of how they intertwine interesting reflection structure, interesting Z2 actions. And I was also supposed to work with functors that weren't just arbitrary equivariant functors, but that had some extra data of how they took things I wanted to call positive to things I want to call positive. And then their theorem is that if you add all these words correctly, the theorem is that, and actually I think this theorem is not as strong as the theorem should be. You really can get their theorem is that if you look at the space of dagger functors or of reflection positive functors from oriented n-dimensional bordism to IZ, that those spaces are indeed a spectrum, and they're a spectrum you knew. Those were the spaces in the spectrum of just the stable bordism spectrum. I want to say, by the way, this is a statement about, I wrote it at the level of just homotopy groups. They have a theorem at the level of spaces. It is not that it parses to ask, if you read their paper carefully with the right classes on, it parses to ask for the spectrum of all maps from here to here. And this is not true at the level of spectra. There are sort of negative homotopy groups on the left that don't match the negative homotopy groups on the right. So there's sort of more to do. But and there's some magic in their proof. The reason is because their proof at exactly one step requires something about IZ that's not true in general. So, okay, so anyway, now I'm going to switch gears. That was my warm-up. That took me, what, a third of my time. Okay, so let me completely switch gears and do a different approach. So what was the point? I told you sort of a good reason why you might believe this conjecture that says that invertible phases are classified by dual to bordism, because it's a theorem that invertible phases of field theories, of sufficiently unitary field theories are classified by bordism. Okay, so let me switch gears completely and forget all about bordism categories and just do some pure algebra. So, well, sort of one of the things that was something Konstantin talks about and that David will talk about tomorrow is how do I want to say this? So let me just do the following kind of very ad hoc, very simple-minded thing, which is I'd like to sort of talk about the sort of smallest thing that deserves the name n vector spaces. And the smallest thing that deserves to be called n-categorical vector spaces would be what I'd get if I took like just the complex numbers, made it into an n category, so made it into I think that's what Konstantin was calling an anti-category, and what I think the current fad is to call categorical spectrum. So I make it into an anti-category, just making it going like, just by putting, Konstantin, I like this analogy, said that means that the complex numbers are just sitting on the surface of the ocean and you have to put sort of icebergs underneath it. And all I'm going to do is I'm just going to sort of set it on top of a turtle, and then I'm going to put another turtle underneath and just sort of do the smallest little thing. So I sort of can build, like, so for any symmetric monoidal object, in particular for any commutative ring, there's an anti-category that just goes turtles all the way down. And then I can do a very simple-minded completion to this, where I just sort of simple-mindedly add in direct sums, simple-mindedly add in what you could think of as like the images of idempotence, or you could think of them as Eilenberg-MacLean objects for monads. Our physics friends call these the condensations. I'm not going to go into the details of that in real time, but please talk to me afterwards if you're. And what you could end up with is a thing that a categorical spectrum that deserves the name vec n. And then it parses to ask about the invertible objects, invertible morphisms in that. Um, and the point is, because it's so, to construct this categorical spectrum, you do very, very simple-minded, very easy to implement things. And so it should be easy to and so it shouldn't surprise you that objects and morphisms in this kind of simple-minded n vector spaces, I do know how to take in one of those and output a nice lattice model. It's some version of kind of commuting projector Hamiltonian. So I'm not saying that my vec n is like all bosonic lattice models. It's just the ones that I'm really good at writing down. But it is a nice kind of categorical spectrum. Okay, so maybe instead of trying to work out exactly all invertible phases, I'll just try to work out the invertibles of the invertible easy phases. Yeah, question.
How is this related to like Morita categorification, for instance?
So the question I don't know if the mic picks up, but the question is, how does this relate to Morita categorification? Constantine mentioned that there should be a construction that's like iterated alg. And if you if you just write down that you want algebras and bimodules, if you just if you open up your kind of undergraduate algebra book and look at what an associative algebra is, it might tell you, it probably won't tell you what a bimodule is because it's an undergraduate book, but pretend it did. If you just try to like take those definitions and ask like, what does it take to be able to compose bimodules? So you can always talk about algebras and bimodules in any symmetric monoidal category. But if you want to do that iteration, you have to talk about what it means to compose bimodules. And to be able to compose bimodules does require a little bit. It requires being able to take geometric realizations. And then if you want to be able to compose bimodules associatively, it requires some compatibility between geometric realizations and tensor products. And if you just take the out-of-the-box definitions of algebras and bimodules and try to iterate this, you lose the compatibility between geometric realizations and tensor products. So you have to actually do something to do this. You have to so the easiest thing you can do is to say, I don't want all algebras, I only want the nice finite ones that were anyway the ones I wanted to write down. And then it does work, and then it exactly matches this construction.
Thank you.
So yeah, so let me so I'll keep writing vec n for my very simple-minded version of bosonic phases, and GM of it for the invertible objects in it. And the sort of idea is I want you to think of this as like a field in the sense of algebra, not in the sense of physics, but in the sense of commutative algebra. That if it's vec n, I want you to think of it as a field of depth n. And if I sort of take the infinite category limit, I want you to think of this as a sort of a field of infinite depth that goes deep into the ocean. And what we've been developing, and also what Tomer and his collaborators have done in a very closely related, slightly different context, is develop a framework for thinking about algebraic closure of deeper objects. And I'm just going to and David will tell us a bit tomorrow about the algebraic closure of this. I'm not going to tell you much about it or how you build it or anything. I just want to make a couple claims about it, which are that this is a nice example of a Galois extension. And so in particular, if you could work out the Galois group of this Galois extension, and if you could work out the invertibles in the algebraic closure, then you would know who the invertibles are before a Galois extension, just as they're the fixed points. So you'd have to work out a lot. You'd have to work out like who's the Galois group and what's the action. And this sort of seems like a stupid thing to do, but you could approach it that way. And I'll just tell you the answers because it's the only way I know how to do it. Yeah.
It was that automorphism. Is that an N group?
Yeah, that's an N group.
N group.
There's two kind of invertible phase. First kind is the one that will gap the boundary. Another is do not live in the gap.
That's right.
So in your theory, it does cover both, or only cover the one with the gap.
So Xiaogang's asking exactly what I mean by invertible phase and boundaries. So as I said, my this vec n is the most simple-minded thing I can think of. It has the fewest things that I can think of. In particular, everything in it certainly has the property that admits a gapped boundary. Now that there might be things that admit gap boundary that are not in it. Like my VecN is like a really kind of simple-minded, I'm not very good at constructions. I'm just writing down the most easy to write down phases. Those are the people in VecN. And if you have any question of like, is this phase there? It's probably not, because it's probably, then if you're asking me about it, it's probably too hard.
So in your case, VecN also contains the one only with the gap boundary. You know, there's some memory or things like
That's
that.
right. So the idea of the VecN is like those phases which sort of have a boundary, which is it's sort of such the boundary condition has very good monadicity, meaning it's like not the zero boundary or something stupid like that. And also if I take that boundary and make a sandwich, then that sort of sandwich has a boundary, and also that sandwich has a boundary, and also that sandwich has a boundary. Those are the things in this guy. And also for like interfaces, you know, an interface has to be able to end sort of in this iterative way. So, okay, so yeah, so where was I? Okay, so let me just sort of give you the answers to this. So let me just start writing Gal for this mysterious Galois group of all automorphisms of my algebraic closure. And then the way we discovered this category that I'm calling W was trying to solve this question of Mike Hopkins of build a category, like engineer a category whose invertibles is isocross. And so it's engineered to have that property. And so I do know the invertibles. Well, at least I know a name for the invertibles. I don't really know the homotopy groups of isocross, but I know their name, and that makes me feel good. So if you ask, yeah, so just formally what you find out, okay, the automorphisms of IC cross is a little bit weird, but the automorphisms that are the identity in pi zero, that are the identity on that C cross, that's equal to the automorphisms of the sphere spectrum, which are sort of orientation preserving. Sort of, I like to call this SL1 of the sphere. Maybe somebody will complain about that name. I'm not sure. Maybe, I don't know. I'm not a homotopy. I learned most of what I learned kind of by people telling me things and not by knowing the correct names for things. So, but I mean the sort of GL1 of the sphere has two components, and I mean the identity component of GL1 of the sphere. That's what I mean. And so just formally, you just discover that my Galois group, whatever it is, I haven't told you what it is, does have a map to SL1 of the sphere. And if you never knew what a manifold was, but still were trying to do Thom spectra, you might think that anytime you have a map to GL1 of the sphere, there's a thing called Thom spectrum for that map, which is just some formal construction about sort of fixed points of actions on spectra. And so if you learned manifold theory only after the fact, by first learning all of category theory and then learn manifold theory, you would have thought this was the definition of Thom spectrum, and you would have thought that there was a thing called M of Galois, the Thom spectrum of this cyclotomic character. And so I'm telling you, just to summarize, I'm telling you that just it's formal nonsense once you believe me that this object exists and that it's a Galois extension. It's formal nonsense that there's some group Gal and some action on the dual to sphere, on the sphere, such that the invertibles in this simple-minded category are the Thom spectrum for that group with that. And maybe we'd be winning if this group was the special orthogonal. That'd be sort of, I'd pat myself on the back and say I'd proven Alexi's conjecture. Unfortunately, it's not. But I can tell you we've been studying this group very well, and I'll tell you what we know about this group, or I'll tell you some of it. So what we've learned about this group is that there's a fiber sequence, almost fiber sequence. There's a complicated story here that I'm not going to go into too much. But I understand very well this sort of the cofiber of this map from the Galois group to the automorphisms of the sphere. And it's a certain L theory. And it's not quite in certain L theory, it's wrong in like 1 degree in dimension 4. And for those of you who knew what a manifold was before you knew what a category was, there's a sort of a very, very similar statement from manifold theory, which is called surgery for framed manifolds. And it says that you can take the sort of the automorphisms of the sphere. This has a map to a different L theory called the signature. That's the name of that map. And the fiber of that map is not quite, but almost the group of automorphisms of piecewise linear automorphisms of R infinity. And again, it's not quite, it's off in dimension 4. And the reason everything's off in dimension 4 is because the reason why everything's wrong in dimension 4, it's because exactly in dimensions sort of around 4, 3 and 4, you have problems with non-abelian knotting, sort of non-abelian knottedness. So when you actually, so our theorem versus the surgery theorem, like neither of them implies the other, but the proofs are the same. In both cases, the proof involves going and doing some sort of sequence of simplifications. And the simplifications involve being able to like take links and simplify them. And as long as you're in high enough dimension, you then know that you sort of use some statements about how linkings are sort of, you can at least simplify links until they're abelian in a certain sense. So there's a version of this that's not about manifolds. The thing in this sort of where it's going on in dimension 3 and 4, 4 is 2 plus 1 plus 1. And the 2 is twice the dimension in which there's non-abelian homotopy groups. And so there's the same somehow, at the end of the day, it's the same non-abelianness that's in homotopy theory in dimension 1. And all higher homotopy groups are abelian. It's the same sort of, at the very basics, the same origin of it. The difference is that in manifolds, you have to think both about a thing and its normal. And so there's the doubling of dimension. Okay, so actually this means that the Galois group should look really, really similar to the piecewise linear group. It's not because the L theory is different and the comolet, the sort of failure in dimension 4 is different, but that's really, really close. So I'm doing great on time. Okay, so where did the piecewise linear group come from? That sort of came out of nowhere. I was telling you this story, pure algebra, just about like Galois theory. And then all of a sudden I was like, hey, this thing's almost the piecewise linear group. So who in algebra could know the piecewise linear group? So let me sort of give you some of that. So by PLN, I mean the piecewise smooth with piecewise smooth inverse homomorphisms of Rn. That's the definition of PLN. The definition of On is the smooth version of that. And you're going to be like, that's not On. On's about rigid transformations. And I'm going to be like, it's about, I'm a homotopy theorist. So, and by SPL, I mean the orientation preserving ones. PL, I just mean the stable limit. And a nice remark of Lurie's somewhere in his cobordism paper is the observation that there's this very, very big, hard subject called smoothing theory, which is part of like actual hard differential topology. And one of the side effects of that hard subject is here's two different categories you can build. You can build the category of smooth framed, well, it doesn't matter. You can build the category of smooth bordisms with like smooth manifolds and smooth bordisms between them, or piecewise linear manifolds and piecewise linear bordisms. And if you just say manifolds, and then these are different. But it makes sense to talk about framed smooth manifolds, and it makes sense to talk about framed piecewise linear manifolds. And if you do the framed versions of these, you can have the framed smooth bordism category. You can forget it to the framed piecewise smooth bordism category. And smoothing theory maybe is equivalent to, certainly is sort of implies that forgetful map is an equivalence of infinity n categories. So what that tells you is that any time you say framed bordism, you don't have to track whether you meant smooth or piecewise linear. And special to the framed case, it's not true as soon as you change the word frame to anything else. So what that tells you in particular that all piecewise linear transformations of Rn act on the n-dimensional bordism category, just by changing the piecewise linear framing. And then Lurie has a one-sentence comment. And as far as I can tell, the proof of this is written in like private emails to people. Actually, if you can then use the cobordism hypothesis. This is a nice application of the cobordism hypothesis. An application of the cobordism hypothesis tells you that this map from PLN to automorphisms of the n-dimensional framed bordism category, that map is an isomorphism. And actually, it's not true in dimension 4. While it's open in dimension 4, it's equivalent to an open conjecture in dimension 4. So there's sort of also some, like, a bunch of statements in manifold theory buried there.
So what is it equivalent to?
It's called the smooth Schoenflies conjecture. But don't ask me what that means. Okay, so from this vantage point, if you sort of, again, if you're the type of person who grew up knowing what a category was before you knew what a manifold was, then you might have asked, like, why would I have ever thought smooth manifolds had anything to do with these problems? I like finite dimensional things. I like dualizability. Implicit in the theory of dualizability is piecewise linear stuff. Smooth stuff is like weird from that perspective. So, so that's my sort of second piece of evidence. I can say, I only sort of have a little bit of time, so I'll say a little bit more. So in dimension 1, the orthogonal and piecewise linear groups are the same. They're just both Z2 groups. Z2 acts on the collection of all categories. It takes a category to its opposite category. It's a sort of easy thing to point out. And the fact that it makes sense to talk about the opposite category, together with the fact that if you have a groupoid and take its opposite, you haven't done anything. Those two facts together are what it takes to talk about Dagger categories. Those are the facts that sort of, or what it takes to talk about reflection positivity in the sense of Freyd and Hopkins. Like, once you know those two facts, there's sort of the rest of the machinery gives you a definition of Dagger category. So what we did with an alphabet soup of people was to we conjecture that this theorem of Lurie's about bordism categories has a sort of non-symmetric version of it. And our conjecture is that if you take the collection, if you take the infinity category of whose objects are infinity n categories with adjoints, that there's some well-defined infinity category of those, the automorphism group of that infinity category we conjecture is this group PLN. Like, I should say, we don't even, it's even a conjecture that there isn't, right now, given the status of what we know and don't know about n categories, it's even a conjecture that there is a map between these two groups. If you had a good tangle hypothesis, you'd be able to write down this map. If you had even a good tangle hypothesis would have trouble proving this conjecture, but that's the conjecture. And if you believe this conjecture, then you could sort of input this characterization of n categories with adjoints into the same machinery that outputted the definition of Dagger category. And what we do in the paper is we run that and output a definition of higher Dagger category, or deeper Dagger category. And my conjecture is that my category W is deeper Dagger. So the content of this conjecture is that this similarity that I told you between the Galois group and the piecewise linear group is actually kind of interpolated by a homomorphism. So I don't know as a theorem any actual comparison between these two exact triangles. Like, I can sort of match their elements, but I can't match them coherently right now. So,
Could you
Yeah.
remind me of the Lurie's statement about PLN?
Lurie's statement is that the automorphism group, well, right, so Lurie's statement is that the free category and n-dualizable object, the automorphism group of that thing is equal to this thing from differential topology called PLN.
What's the difference between the
So,
could you remind me?
and the conjectured statement is, so this was about, the Lurie statement is about the specific thing called the free symmetric monadal n category on a dualizable object, thought of as its automorphisms in the category of symmetric monadal n categories. And here I'm talking about the infinity 1 category whose elements are arbitrary, not necessarily monoidal n categories with adjoints. They're sort of the two statements should sort of inspire each other. So there is a theorem that you could do. There's a relation, which is that the way you would try the reason why we think this conjecture has a good chance of being true is we think that there's a good diagrammatic calculus for n categories in high dimensions. I know that Lucas and his collaborators are working on developing that calculus. And if you did have that calculus, you would at least have a map from PLN to this group of automorphisms of this. And
Not use this, the what hypothesis one.
in the best of cases, you would just write down a diagrammatic calculus. This is sort of the what you might think of as like an Ayala-Francis approach to the cobordism hypothesis. The best case is you would write down diagrammatic calculus. You would develop all of category theory in terms of diagrams on manifolds. And then the cobordism hypothesis would just fall out of that. And in particular, if you had a diagrammatic calculus for n categories without symmetric monadality, it would imply something about categories with symmetric monadality, because that just means you've sort of stabilized and given yourself infinitely many normal directions. And then our conjecture would basically, well, it would at least imply the part of the Lurie theorem. But I don't know, ask Lucas for details because he's thought about them more than I have. So, okay, so yeah, so let's see if I can sort of finish what I wanted to say. I think this is the closing thought. I think I'm going to end early, which so this is what we're working. One of the things we're working on right now. So this category that I told you, this sort of very stupid, not stupid, but very simple-minded thing about kind of just writing down the simplest phases is definitely the wrong thing. Like it's not, most phases of matter are not given by commuting projector models. Most phases are somehow not in this construction. My constructions right now that I told you about with the sort of like universal target category, they're in some sense too finite to be matching actual phases of matter. They're great for doing algebra, but they're too finite for actual phases of matter. So for instance, I'm only capturing things that have like, in a certain sense, that are kind of commuting projector. And I don't even have, I'm not even claiming I'm capturing all things that are commuting projector. I probably am, but I don't know how to prove that. So there should be a more general construction. I think also Jackson referenced this sort of in the first talk. We sort of think that there's a better construction that's more analytical of these things. And analysis, like functional analysis, is already inviting you to think about adjoints and dagger categories and so on. And so if we did have a more analytical version of, I forget why I said this on the slide here about univalence, you can ignore the orange stuff. If I did have a more analytical version of this construction, I could still hope that it has this version of this kind of like this notion of dagger category that we worked out. And in particular, if it did, it would from just the construction, if it were like just from being dagger, having all this sort of Hilbert stuff, you would have a nice comparison map between the piecewise linear group and whatever the Galois group of this more analytic object is. And then, so that you'd have to do that. And then the next thing you'd have to do, like then as soon as you have a comparison map, you could hope that that comparison map's an isomorphism. And so I'm going to say, like, that's my conjecture. That's how I think this stuff would work. And if I could do that, that would be the way to prove this kind of Kitaev, Kapustin, well, at least this sort of piecewise linear version of it would actually characterize invertible phases. So this is my proposal for how one could prove this. I'm not saying I have any proof of it. And this is also why I believe that there's a chance that you're getting like piecewise linear bordism, and there's no chance you're getting smooth. Okay, so I thank you for your time.